Hello everyone, welcome to the third video on Simulink model for electrical circuits. In this video, we will discuss about the three-phase AC circuit specifically for a RL balanced load. Okay, so the circuit which we have is given here. So basically, we have to implement it in Simulink model. Uh, and basically it is a star connected source and load. Now on the source side, the specifications which are given, the voltage is 230 volt. So this 230 volt is the RMS voltage. Okay, and each of these voltages, they are at 120 degree. They have a phase difference of 120 degree. The frequency is 50 Hertz. On the resistive inductive load side, the value of resistance is 10 ohms and the value of inductance is 40 millihenry. So we have to implement this circuit in Simulink and we have to calculate the line current, the phase impedance, the phase voltages, and the apparent active and reactive power. Okay, so let us go into Simulink and try to implement this circuit. Okay, so to implement this three-phase circuit, first of all, we will need three AC supply. Okay, so AC voltage supply. So since it is a three-phase circuit, so we will need three of them. Okay, so I am going to rotate it. Okay, there we go. So I can copy this, but before copying it, what I'm going to do is I'm going to change the parameters. So the 230 volt is the RMS value. So since in the parameters we have to feed in the peak amplitude, so we have to multiply it with square root of 2. So we can do that by simply using the function sqrt and 2. Okay, the frequency, the supply frequency is 50 Hertz. Okay, and the phase difference, so each of the voltage source, they have a phase difference of 120 degree. Okay, so we are going to change it, but we'll leave it this one for the time being. Okay, now I will copy it and paste two more of them. Okay, something like that. Okay, so the first one will have a phase difference of 0 degree. Now the second one, I'm going to change the phase angle to minus 120. Okay, and the third one, I'm going to change it to plus 120. So all these voltages, they will have a phase difference of 120 degree. Now the next thing that we have to do is we have to connect it in star configuration as shown in the circuit diagram. So we have to look for ground, go down and select this one with three lines. Okay, this one. Now we can connected to the ground, like that. So this has arranged the voltage source in star connection. Okay. Now the next thing we need is 3 RL branch. Okay. So series RLC branch. Okay. So we will use 3 of them. Okay. So before using them, I am going to change it to RL, or before copying them, I am going to set the parameters. Okay. So the resistance, it is 10 ohms. Okay. And the inductance, it is 40 millihenry. So it will be 40 e to the power minus 3. Okay. Now I will need 3 of them. So they are again connected in star configuration, the load side also. Okay. So again, I'll have to connect one of the terminals all to ground. Okay. So another thing what I can do is I can group them together. Okay. So by using this area option, I can just place it here, and then I can change the dimensions like that. Okay. On the sides. Okay. So that's my 3-phase voltage. Okay. So using annotations, I can write it as 3-phase star connected supply. Okay. And similarly, I can group the load as well. Okay. And label it. Okay. So 3-phase star connected load, RL load. Okay. Now the benefit of grouping them is I can move them, all 3 of them together, or all the components which have been grouped together, I can move them together. Now the next thing is I need to measure the line current. Okay. So I need current measurement. Okay. So again I will need 3 of them. Right. So I can say this is my I1 and then I2 and I3. So I can again copy it and paste it. So after doing that, I can I would then need the RMS blocks and a display. So what I'm going to do is, so since I will need 3 RMS blocks, so again before copying it, I'm going to change the fundamental frequency to 50 Hertz. Okay, and copy 3 of them. Okay, and I can connect the 3 something like this. Okay. Now you can use 3 display uh, to display the individual currents, but this time I'm going to do something different and use a single display, and that single display will be able to display all the currents. Okay, so I can change it to line current. Okay, so to do that I will need a multiplexer. Okay, so let's choose this one. So this is my multiplexer, and I will change the number of input ports to 3. Okay, because I have 3 inputs, and then connect the inputs. Okay, so I'll just make it a little better. Okay, and turn on the block name. Okay, so this way if I connect using a multiplexer, I can display all the line currents on a single display. Right, we'll have a look at it. Now we may also want to check out the scope or the waveform. So let us look for scope, and let's do the same thing again. So again you can change it to 3 number of inputs or 3 channels for the scope, or we can use this multiplexer. Okay, and for the scope or for the waveform I will need the uh, continuous values of current, not the RMS value. Okay, there we go. So this is my line current. Okay, the oscilloscope for line current. Okay, now what we can do is we can add the power GUI and simulate the circuit. Okay, so all the phase and everything is set. Now The frequency is 50 hertz again. So let's check this time. Let's check the output for or the waveform for 3 cycles, right? So we the stop frequency should be 0.06. Okay. Now let's try and run the circuit and just check the output. So if we expand this display, we can see we have the three currents. So the three currents ideally they should be equal. They should be 14.33 or 32, all three of them. Okay, but maybe because of the Simulink calculation, there is a slight difference. Okay, now let's also check the waveform, the three waveforms. Okay, so um, all the three currents they have a phase difference of 120 degree. So you cannot display it on three different scales or three different graph because we have used a multiplexer and it's on a single channel, right? So that is not possible. But you can still measure the the phase difference between the three, okay, using the cursors. Now next we need to measure the voltages. Okay, so we will need voltage measurement and we will need three of them. Okay, so I will have to move it a little down. So let's say somewhere here. Okay, uh, so this will be my, you can say V1 or the first phase, and similarly I can copy and paste two more of them. Great, V2 and V3. Okay, now the the positive terminal of this of these voltage measurements, I can connect them to the lines, but the remaining, the negative terminals, I have to connect it to ground. Okay, so let's search for the ground, and it usually appears at the bottom. So this is the one. So I'm going to connect the negative terminal to the ground. Okay, and this one as well. And I can connect the positive terminal to the lines. So the first line I can connect it like that, the second line and the third, right? So these will give me the phase voltages. So again they are continuous, so I will need the RMS block. Okay, so again I can change the fundamental frequency to 50 hertz, and need 3 of them. Okay, and I can connect them like that. Okay, so calculations can be individual, but the display can be combined together using a multiplexer. Okay, so let's again use a multiplexer. It's better. So again, let's use this multiplexer. Change the number of inputs to 3 and oops, and let's zoom in a little and make the connections. Okay, and lastly we'll need a display. Okay, so display, a number display, which usually comes at the bottom, and we can connect it to the display. Okay, so let's now run the circuit. So we have already checked the line currents. Let's now check the phase voltages. So again there is a slight difference, but near about they are all 230 volts. Okay, so let's go back to the slides and verify all these values using calculations. So in the slides here I have done the calculation. So again I've calculated the inductive reactance XL, and then using that XL I have calculated the impedance Z. Okay, that comes out to be 16.06 ohms. Now using this value I can then calculate the phase current. So the phase current, it comes out to be 14.32 amperes, near about the same value which we were getting in Simulink. Okay, and we also need to calculate the powers, so we'll come back to that. And the phase voltages, they are 230 volts. Okay, now let's try and implement this power. Now coming back to the circuit or the Simulink again to implement power. So this time let's look for active power. Okay, to calculate the active, reactive and all the powers, let's look for this. Now if we go down and look for this one, power 3-phase instantaneous, and drag and drop it onto the main screen, something like that. Okay, let's turn on the block name as well. Okay, now if we zoom in to this block, you can see that one of the terminal is for voltage ABC and another one is for current ABC. So ABC means all the 3 phases. Okay, so I have already combined the current using this multiplexer. So I can connect the current to here. Now similarly, I would need to combine all the voltages after the voltage measurement. So I would need a multiplexer again. So let's search for mux, and maybe here, and then let's change the number of terminal to 3. Okay, and I'll have to zoom in a little bit to do the connections. So let's connect them one by one, something like that, and the next one, and the last one. Okay, so I have all the voltage measurement which are connected to this multiplexer, and then from here I can connect it to the voltage. Okay, uh, so again these are all continuous or analog power measurement. So I would need the RMS block. Let's search for true RMS, and we have to change the fundamental frequency to 50. Okay, and we can copy and paste another one. Okay, and finally we will need a display. Okay, so a number display. Let's go down and select this one. Okay, copy it and oops, copy it and paste. Okay, now so this one is going to display P. Okay, and this one is displaying Q. Right, now before I run the simulation or the circuit again, I want to change something. So that is your numeric display format. So I want to change it to short E. So it will display in power of 10. Okay, so these values are going to be very long values. So it's better to use this format. Okay, now let's run the circuit. So as you can see, the P is coming out to be 6.153 10 to the power 3, and Q is 7.732 10 to the power 3. Okay, let's now verify them using the calculations. So if we come back to the slides, we can see that the active power is 6150, right? It was 10 to the power 3, so it's near about the same value. And reactive power Q, it's coming out to be 7732, again 10 to the power 3, 7.732. It was somewhere around that value it was coming. So again, the measured values and the calculated value, they are quite close enough. Now for apparent power, you can implement it in the Simulink, but basically we'll have to implement some mathematical blocks to do the calculations. Okay, so basically we have to take square root of active power square plus the reactive power square in Simulink, right? Another simpler way is to uh, do the calculation, right? So from the calculation, the apparent power, it's coming out to be 9882.70, right? So this was all that I wanted to discuss with you in today's video. Uh, in the next video, we'll discuss or we'll try to implement a three-phase unbalanced RL load. Okay, so we may use the same circuit and change the loads, the value of the loads. Okay, so that's it for this video. Thank you so much for watching and see you in the next video.